In the previous class, we got an introduction to what is frequency modulation. We have derived the equation for the modulation index of a frequency modulated signal. We have understood the basics of frequency modulation. In this class, we'll do some related problems. What kind of problems that is possibly going to appear for your exams and how to solve them. Okay. So before we go into that, we'll see a small comparative statement between phase modulation and frequency modulation. In case you are asked to give a comparative statement, you can use this. As I told you, this is a possible question when you are asked to compare phase modulation with frequency modulation. You can write these points so that you get maximum marks out of it. First point is about the instantaneous phase. In phase modulation, instantaneous phase is given by 2 pi fct plus kp m of t. In frequency modulation, the instantaneous phase is given by 2 pi fct plus 2 pi kf integral 0 to t m tau d tau. So AC stands for the amplitude of the carrier signal, Fc stands for the frequency of the carrier signal, Kp is phase sensitivity factor and Kf is frequency sensitivity factor. You should be capable of defining what is phase sensitivity factor and frequency sensitivity factor. Similarly, instantaneous frequency Fc is given by Fi of t is given by Fc plus Kp d by 2 pi d tau mt, dt mt. We have already seen that frequency modulated signal, the instantaneous frequency, this is very important, Fc, the carrier frequency plus Kf, m of t. So the output modulated wave in case of phase modulation is given by AC cos 2 pi fct plus Kp m of t. Whereas for frequency modulated signal, the output modulated wave is given by AC cos 2 pi fct plus 2 pi kf0 to t integral 0 to t m tau d tau. So we have considered three important factors for our comparison: instantaneous phase, instantaneous frequency, and the output voltage, output signal, S of t. Now we'll see some very simple problems. A signal is given, x of t is equal to 2 cos pi into 10 raised to 4 t V. The signal is applied to an FM modulator with the sensitivity constant 10 kilohertz per volt. Find the modulation index of the FM wave. How will we find out the modulation index? What is the definition for modulation index? Any one of you please tell me what is the definition of modulation index beta? Beta is equal to delta F by FM. Very good. What is delta F? What is delta F? Frequency deviation. What is that? Kf into AM by FM. Now Kf is given as 10. Kf is given here as 10 kilohertz per volt. AM if you know and FM if you know, you can calculate beta. Both these things you will get it from this equation, right? Yes or no? How will we calculate the modulation index of the FM wave? You're asked to find out the modulation index of this FM wave. So the output instantaneous frequency is given by Fc plus Kf am cos 2 pi FMT. Kf is given in your Kf is already given in your question. So from the question you will get the value of am to be 2 volts. We have for the input signal is here, am is here 2 volts. Omega m, that is 2 pi f, is pi into 10 raised to 4. So from that you can calculate Fm. 2 pi omega m, the value of omega m will be 2 pi Fm. 2 pi Fm. And omega you got it to be pi into 10 raised to 4. And from that you got Fm. And you substitute in the basic equation for modulation index. And you get the value to be 4. Shall we do the next problem? Any queries? The next problem, a 10 megahertz carrier frequency is modulated by a sinusoidal signal of 500 hertz. The maximum frequency deviation given being 50 kilohertz. The bandwidth required as given by Carson's rule is, what is the bandwidth? The question is you have to find out the bandwidth. How will you find out the bandwidth? Can any one of you tell me the equation for finding out the bandwidth of a frequency modulated wave? We have already seen that the bandwidth of a frequency modulated wave is given by 2 into beta plus 1 into Fm, or in other words 2 into delta F plus Fm. Okay, delta F frequency deviation is given in the question to be 50. Fm already given 0.5. So the bandwidth is 101 hertz. Very simple direct question. Frequency deviation is given. Modulating frequency is given. You need to find out the bandwidth. All of you understood? So let's go to the next problem. Next problem. Determine the modulation index and plot the sinusoidal FM wave for which EC max is equal to 10 volt, EM max is equal to 3 volt, K is 2000 hertz by hertz per volt, FM is 1 kilohertz and FC is 20 kilohertz. Basically different books use different nomenclature, and whenever you have a C as a suffix, it means that it is a carrier wave, and M for the message or the wave which we are going to modulate. Okay, so you are given V max, V C max and V M max to be 10 and 3. Okay, so you are asked to find out the modulation index, and then you are asked to plot the sinusoidal FM wave. On the same axis, plot the modulating function also. The plot should extend over 2 cycles of the modulating function. First, we are going to find out the frequency deviation. Frequency deviation, you know, delta F is given by Kf AM. Kf is the frequency sensitivity factor, that is 2000, that is already given. AM is 3 maximum amplitude of the modulating signal, so you got it as 6000 Hertz. So from that we have found out the modulation index beta, like the previous problem what we have done. So delta F by Fm 6000 by 1 into 10 raised to 3, that is equal to 6. The next part of our question, we were asked to plot the sinusoidal function. So the functions to be plotted, first one is a message signal. So we have AM cos 2 pi FMT, we have determined FM here. So we got this is equal to 3 cos AM is given to be 3, 2 pi into 10 raised to 3t. Similarly, the output signal, output modulated signal S of t is given by AC cos 2 pi FCT plus 2 pi integral 2 pi kf integral 0 to t m of t dt. This is the equation for the output frequency modulated wave. So what are the functions that are to be plotted? First one is m of t, second one is s of t. On substitution of necessary values, that is fc, kf and m of t, you get this output signal of the frequency modulated wave to be 10 cos 4 pi 10 raised to 4t plus 6 sine 2 pi 10 raised to 3t. Are you all able to understand how we got these equations? So we have got both the equations and we are going to plot this graph. As we go on, we will be doing more solved problems in the classes, but I'll be sharing with you more questions which you can do as practice for your exams. We'll be solving all the previous year question papers from almost every university. Different universities question paper we have. We have a question bank. From the question bank, almost all questions or whatever is possible from our end, will be solving it out in the future sessions. So you can refer to these for more questions. But due to limited time, now we'll be proceeding with the next topic. There are two types of frequency modulated signals. So we'll divide the entire frequency frequency modulated signals in two extreme cases. The first one, we'll call it as narrow band, where the modulation index is very small, less than 1, and wide band, where the modulation index is much greater than 1. We have two cases, narrow band FM and wide band FM. The name itself gives you a big hint. Narrowband means the modulation index, frequency deviation, everything is much less than 1, while the wide band you have a large modulation index, the bandwidth and everything relatively to be higher. To begin with, we'll see what is narrowband and wideband with their respective spectra. Let us consider an FM signal which is given by S of t is equal to AC cos 2 pi fct plus beta sine 2 pi fmt. So this signal using trigonometric relations can be split into two. One the cos part and the other one is the cosine part and the other one is the sinusoidal part. Easy to remember. AC cos 2 pi fct cos beta sine 2 pi fm t minus AC sine 2 pi fct sine beta sine 2 pi fmt. Now for a narrowband frequency modulated signal, what happens is that cos beta sine 2 pi fmt will be approximately equal to 1, so that this part is 1. Sine beta sine 2 pi fmt, this is also, since this is a very small, as it approaches 0, we can approximate this to sine theta when theta is approaching 0, or limit theta tends to 0 will be theta, right? Yes or no? So instead of sine beta 2 pi fmt, we are approximating beta sine 2 pi fmt, and we get the equation for a narrowband frequency modulated signal. Okay. So an FM signal for narrowband signals will be AC cos 2 pi fct minus beta AC sine 2 pi fct sine 2 pi fmt. So this particular equation what you have written defines the narrowband FM signal produced by a modulating signal. M of t is equal to AM cos 2 pi fmt. So this particular equation, or this last two slides, derives the equation for a narrowband frequency modulated signal. This could be a derivation question directly, or there could be problems based on this. Quite simple and easy to understand. Very easy derivation, right? Nothing is difficult here. We have used only trigonometric basic trigonometric equations. Right? Any queries? Shall we proceed? So now how we are going to generate a narrowband FM signal. The block diagram for generation of a narrowband frequency modulated signal. We have an integrator here, product modulator, and we have a phase shift, and the output you will get. This is a carrier wave oscillator. We have a crystal oscillator here, which generates the carrier wave with a frequency FC and an amplitude AC. With a phase shift, we are getting it into a product modulator. Product modulator is the heart of the narrowband FM generator. So questions can be like this: with the help of a neat block diagram, explain how narrowband FM signals are generated. In that case, you can use this block diagram. You have an integrator, product modulator, summer. The output you get it as a narrowband FM wave. We look into the phase diagram of a narrowband FM signal in the next slide. So this is the basic phasor diagram for generating a narrowband FM signal, and this probably almost a very important question that would appear in your university exams with a neat phasor diagram for generating narrowband FM signal. Explain the advantages or explain how narrowband FM signals are generated, or what are the advantages of using narrowband FM signals where the modulation index is presumed to be much less than 1. Now considering a situation where FC is large enough, that is, we are going to study how wideband frequency modulation systems work. We have the same equation for the frequency modulated wave output. S of t is equal to AC cos 2 pi fct plus beta sine 2 pi fmt, the same equation as written before. Now we are considering only the real part because this is a complex number. We are considering only the real part of this one, where we have made this cos plus sine into e raised to j 2 pi fct plus j beta sine 2 pi fm t. Considering the real part, this can be written as AC e raised to j beta sine 2 pi fm t. This particular element is eliminated. So this particular S of t is called as the complex envelope of the frequency modulated signal. So S of t, which is given, is the complex envelope of FM signal. Since it is a periodic function, it can be written as a function of time. S of t is equal to sigma n is equal to minus infinity to infinity Cn e raised to j 2 pi nfmt. Have you understood? Any doubts? So let me proceed. So we have defined this as the periodic function of time. Now this term Cn will be defined as Cn is equal to Fm integral minus 1 by 2 to 1 by 2 Fm to 1 by 2 Fm S of t e raised to j 2 pi n Fm t. The term Cn is defined as, now this part, the first thing you have already written in the previous slide, this one. So here you are defining what is Cn. Okay. So on expanding Cn, Cn is equal to, we already have defined that Cn is equal to Fm minus 1 by 2 Fm to Fm 1 by 2 Fm S of t e raised to j 2 pi n Fm t. On expanding this, we'll get Cn to be AC by 2 minus pi to pi e raised to j beta sine x minus nx, where we are defining x to be 2 pi n Fm t. Is that clear for all of you? Any doubts? In mathematics or in engineering mathematics, you might have studied Bessel's function. How many of you remember that? Do you remember what is Bessel's function? Anybody? Here we are going to see a practical application of Bessel's functions. So this is how a Bessel's function might look like. An nth order Bessel's function with the argument beta is given by Jn of beta is equal to 1 by 2 minus pi to pi e raised to j beta sin x nx. So here what we are doing is that we are simply substituting this nth order Bessel function here to get the value of the final value of Cn. So these are the important equations that you have to remember. What is Cn? S envelope of T, and on substituting the value of Cn in S envelope of T, you get S envelope T is equal to n from minus infinity to infinity AC Jn beta e raised to j 2 pi nfm T. So after this, we'll get this expanded here so that we can conclude with the final S of t. So here, this equation, we take up the real part of S of t. So we get the real part here, AC is a constant, the carrier amplitude is taken outside, and the real part of n minus infinity to infinity, Jn beta e raised to j 2 pi Fc plus n Fm t. On further expansion, what you get, S of t is equal to AC summation n minus infinity to infinity Jn beta cos 2 pi fc plus n fmt. So from this, converting this into Fourier domain, converting this into frequency domain, we get S of f is equal to AC, n is equal to minus infinity to infinity, Jn beta delta f minus fc minus nfm plus delta function of f plus fc plus nfm. Quite very easy to remember, right? This is the equation for the wideband frequency modulated signal. So in today's class, we have derived the equations for narrowband frequency modulated signals as well as wideband frequency modulated signals. Apart from this, we have seen some solved examples, very simple problems in frequency modulation. And with this, I think we have completed frequency modulation and we'll be going into the next topic in the next class. So thank you all, thank you very much.